Alrighty, now we are going to wrap up chapter 8 today. As far as new material goes, on Friday, we are going to do one of my favorite labs. I really like this one. It's Lab 10. Make sure you come to class prepared. What, England? We're not blowing stuff up, but we are getting to see, stuff from the real world. We're going to work with dialysis tubing, and you're going to selectively permeable membranes, things like that. It's actually really cool from a science standpoint. So yeah, you got to be in here all year to blow shit up. Sorry. Okay. Try to weed all those other kids. 65% rule reads all the kids. I don't want to, have the joy of blowing stuff up. So.
Before we blew something up, I'm just like, yeah, I can't take it no more.
Well, problem is by then it's too late. That deadline's like in 2 weeks. So. Yeah, it'll happen. Yeah, I did the same thing I did a few months ago. I'm pretty sure it was Trotta. Yeah, sorry. I don't know why that is. I don't know. You guys remember the day I kept calling Dalton Trotta?
Yeah.
You guys remember that? Yeah, so she came to the door. I'm like, I thought you were sick today. And I realized Trotta was the one that emailed me. I don't know what it is. I think it's being a parent so much, crap for brains. Yeah, that was a statement about teenagers in case you didn't pick that up. Yeah, okay. Alrighty, so this is Chem 1110, Chapter 8, Day 3, and this is pretty our objective. I'm going to be honest, our objective's kind of weak. I'm just going to cover what's most important. And that is to be able to properly calculate dilutions. We're going to do some other things, but that's the biggest part of this, simply because there's a couple of test questions directly related to this on the test. Now, the typical dilution equation is simple. It's M1V1 equals M2V2. Okay? These are my initial molarity and volume, and these two are my final molarity and volume. Now, if I'm going to dilute something, what am I going to do?
Add less non-fat in water.
I'm gonna basically add some water, right? Yeah. Now, typically, an equation like this, what are they going to do? They're going to give me 3 terms. I'm going to solve for the 4th. Wham, bam. I'm done. It's easy, right? Now, what they're going to do, though, is they're going to give you maybe 1 or 2 of the easy kind, and then they're going to give you one of these. Okay, I'm going to give you, we're going to walk through it, we're going to talk about it, and then we're going to solve it. Okay, so the problem is going to look something like this. So, what is the final concentration of adding 82.5 milliliters of H2O to 125 milliliters of a 4.2 molar solution? Okay? Now, what you got to do is you just got to look and say, okay, well, what do I know? Okay? Well, I know I'm going to look for my final concentration, which is I'm looking for what here? I'm looking for M2, right? M2 is what I don't know. Okay, then I say, well, what do I know? Well, what is this 125 milliliters?
That's your initial.
Yeah, that's my M1. What is it? Sorry, that is my V1. Thank you. That's my V1, which makes a 4.2 molar my M1, right? Now I still need a V2, right? And a lot of people say, well, it's obvious this is my other volume, right?
No, it's not.
But that is not my V2.
Because you're adding it.
Exactly. Okay? Understand, most of the time they'll give you your V2 or whatever. In this case, I'm adding water. So I need to find my V2. My V2 is going to be what?
207.5.
But it's going to be what I started with, my 125 plus my 82.5, which gives me what? 207.5 milliliters, right? So now I can set up my equation. I'm going to go 4.2 molar times 125 milliliters is equal to M2 times 207.5 milliliters. Now, M2 is what? Do you not have a calculator in England? Oh, just spit it out. 2.53. Big M? Yeah? Yeah? Why? Yeah. Because that only has 2 sig figs. My answer can only have 2 sig figs, right? So I'm going to erase that 3, right? Now, this is something that, I'm going to be honest, most teenagers are terrible at. No. Yes.
Would you have to multiply like the M2 and the 207.5?
You would, but what they did is they just divided by 207.5 to solve that, right?
Yeah.
Now my milliliters reduce out, give me my M2 by itself, right?
Yeah, I was thinking like multiplying those two together to get like the final concentration.
No. Okay, so it's just molarity is a concentration. That's just it. Okay. Now, this is what I can never convince students to do. Okay. Let me share an example. Let's say I'm in math class, and my teacher asks me to factor a problem, right? We can all factor, right? Well, when I'm done, is there anything I can do to help me figure out whether or not I'm right on my test? Yeah, I can do what? No, I could actually just foil it back together, couldn't I? I mean, right?
Oh yeah, in this example, yeah.
Yeah. So here's my question. Is there a way for me to look at that number and have any inclination of whether or not I could or could not be right?
Yeah, yes. What's up to do that too?
I could, easier than that. Wiser.
Yeah, the M2 has to be smaller than
Exactly. Because I know that my molarity has to go where? Down, because my volume went up and they are in inverse relation. So it doesn't guarantee me that I'm right, but it's a really easy check without doing a bunch of math to say, hey, if that came out to be 9, I better be saying to myself, self, I done screwed up. Because I know it can't be 9. Nobody ever talks to themselves in a foreign language or a different dialect. You know, I talk like my dad. Hey, listen, dumbass. No, my dad was way meaner. No, just kidding. Yeah. My dad was a mechanic. Anybody's dad a mechanic? No? My dad has the strongest hands you will ever see. And he used to do that. You know, when he'd get nobody has one of those parents. And he literally, I thought he had caved my entire chest in once. I had a bruise like this big for a week from you little. No, parents don't.
Yeah, I got it. Yeah.
You know what I'm talking about, right? Man, he was hitting me in the chest, and I'm just like, oh my gosh. Thought my heart was going to explode from his finger just pushing right through it.
Is it because you couldn't hold the flashlight right while he was...
No, but that is a funny meme. I mean, that's the funniest. That is as true as the day is long. So, side note here. You guys don't know my oldest, but when I lived in the Terrace, I was replacing the brakes on my car one day. And I had never done this car before, and the first time you do anything usually doesn't end well, right? And I profaned a little bit. And my kid might have been 3, I guess. And a couple weeks later, I'm downstairs fixing the dryer. And I'm out front fixing it, and he's behind it. And all of a sudden, I hear this. Damn it. And I hear this. Damn it. He was behind it, and he'd pick up a wrench, and he would drop it and swear. Then he'd pick it back up, and he would drop it, and he would swear. My wife looked at me, and she blamed me for everything. And she was right, and I can't dispute that. But I'm like, the only thing you learned What was that? I'm like, I did the entire car. He couldn't learn how to change it, but he can learn how to swear. I'm like, really? Yeah, she's never let me live that one down, by the way. Is that what it was? Oh.
Significantly more useful in a wider variety of circumstances.
That is.
It's not going to be in the middle of the road and have to change throttle.
That is true. That is true. Okay. Alrighty. Now, from there, we're going to talk about a little bit of the lab because it kind of fits in right here. Colligative properties. Now, colligative properties are properties that are properties of, sorry, that's an of. Good thing I got some white out here. Maybe I could go back to that day and just white out all those swear words I used. Maybe my boy would have turned out to be better. Properties of a solution. Actually, he's in law school, so he turned out all right. Mason, on the other hand, that's a different story. Properties of a solution that only depend on the concentration of the solute, not the identity. Now, this is, I don't know, it can be a little bit deceiving because the identity is a little bit important whether or not it dissociates or not. So, for example, if I had, let's say I took this. Let's say I had 1 molar C6H12O6 and I had 1 molar CaCl2. And I put them both in water. I put them both in 1 kilogram of H2O. Actually, wait a minute. Is it water or solution? Let me check. Now I'm doubting myself. Water, I'm right. Okay? And then I'm going to put them both in 1 kilogram of water. Now, what you need to understand is that I have to figure out how many particles I get out. Okay, now sugar, anybody remember what kind of molecule or what kind of particle sugar is? I already kind of gave it away. Sugar is a molecule, which means it bonds how? Anybody remember what sugar is? What kind of compound it is? What? No. That's what it does between molecules. What's inside the molecule?
Is it polar?
No.
Is it non-polar?
No. No.
Or doesn't it have to
Let's look at this. What kind of compound is CaCl2?
But doesn't it have to be polar to dissolve in?
No. Because it will hydrogen bond because it's got H bonded to O's. Okay. That's why I said, that's why water is universal because it does a couple of things. Polar and hydrogen. Does that make sense? Nobody knows what kind of molecule, or not even a molecule, what kind of compound CaCl2 is? It's an ionic. Okay, it's an ionic compound. Okay? Does anybody remember then what kind of compound sugar is? It's a covalent. Now that's important. Okay? Sugar does not do what when I put it in water? It doesn't dissociate. So how many particles will sugar give me? 1. This gives me 1 particle. How many particles does CaCl2 give me?
Gives you 3.
It actually gives me 3 particles. Because I'm going to get what? Because this not only dissolves, because sugar dissolves, it just doesn't dissociate.
Yeah.
Calcium chloride, though,
It's going to give you a calcium 2 positive.
it's going to give me 1 Ca2 positive and 2 Cl negatives. It gives me, do you have her cell phone by chance? Anybody got Trotta's cell phone? Nobody? Because she emailed me and said she was going to get on, but I don't hear her. Ann, are you there?
Yeah, I am.
Okay, just checking. I wanted to make sure you wouldn't get left out. Yes, Trotta, not Dalton, sorry. Okay, so now, this is what happens, and this is what you're going to do in the lab, okay? When you're talking about colligative properties, there's like 4 main ones. There's freezing point depression, there's boiling point elevation, there is osmotic pressure, and there is vapor pressure. Okay? The more particles I have, the more I impact those things. Like, for example, snowed last night, right? Not enough to shovel, but enough to make it slick, right? So most people did what this morning or last night? Yeah, went out and put down some
Salt.
like real salt.
No, like rock salt. Road salt.
Yeah, they just went out there with like their salad. They're like, yeah, this sounds pretty good. No, it's like the blue stuff.
Okay, so understand something. Listen to what she just said. It's like the what?
I said it's like the blue stuff.
The blue stuff. Okay, well the blue stuff ain't
Salt.
salt. It's a salt, meaning it's an ionic compound. But it's called ice melt. And it's not called salt for a reason. Because when people think of salt, there's 2 ways to think of salt. There is a salt, which simply means any ionic compound. And then there is actual salt, which is NaCl. Now, NaCl would give me how many particles? 2. CaCl2 gives me 3. Which one's better?
CaCl.
CaCl2. That's why ice melt is not called salt anymore. Does that make sense? Now, ask me. We good? Now, so here's an example of what I'm talking about. Could I have taken my sugar container out there and spread sugar all over my ice and gotten it to melt?
No.
Yes.
Yes.
Yeah.
Anything will do the trick. It just depends on how well it works. It is. It makes everything sticky. If I use this, it's going to work.
The regular salt. Best.
Compared to sugar, it's going to work
Better. 3 times better.
3 times better. Because I get 3 particles out where sugar only gives me 1 particle out. Yes?
Why does sugar make things sticky?
I'm going to assume if you're talking intermolecular, it's probably because of the hydrogen bonding stuff that it does. Yeah, it's able to stick things together. Yeah.
Sort of like central tension.
Yeah. I mean, we're going to talk about solvation in a minute, which is kind of the opposite of that, but it's the same idea.
Okay.
Now, what you're going to understand... Yo,
Is this true for like, in general speaking, for like all covalent and all ionic?
pretty much, yep. Which is if you look at the solubility rules, most of those things they address are, I was going to say most or all, but I think all of them are actually ionic compounds because of that.
It does say solubility of ion.
Oh yeah, there you go. So it is not most of all, it is all. Thank you. Yes.
So why does ice not continue to erode like your driveway or like sidewalk?
Okay, so that is actually why they use ice melt, not salt. Another reason they don't use salt is because salt is terrible for what? Concrete. Terrible for concrete. You go to a house that used salt for a lot of years, their concrete is literally just starting to fall apart. Okay? Which is why they still use salt on most of the roads, because the roads are asphalt and it doesn't harm the asphalt. Although if you drive I-15, what have you noticed? You guys probably don't, but they're starting to replace a lot of asphalt freeways with concrete. Well, guess what they don't put down on concrete? They don't put salt down. Because I'm going to spend $1 billion building a brand new I-15, and in 10 years, what would I have to do? I'd have to build it again. So yeah, you'll notice they don't use any place that there's cement freeway, they will use something besides regular NaCl. And that's why when you buy ice melt, it's not NaCl anymore. Plus, it's bad for your lawn and bad for a lot of things. Okay? But asphalt, you look at that side of those roads. That's why if you've noticed, the first 3 or 4 feet right off an asphalt road, nothing ever grows. It's just that kind of dirt. Because there's so much salt in that dirt, nothing will grow. If you do that on your driveway, the edge of your lawn will always be dead. So,
You know when you
I'm
say-
teaching you like all kinds of stuff.
Why
Life lessons. I appreciate that. Thank you. Yes.
You know when you say a word over and over and then it just doesn't sound right anymore? Yeah, that's what's happened with salt. This just doesn't sound right.
Well, I mean, it is. It's different. Okay? Alrighty. Now, so when I look at this, and I would say there are a couple of numbers, and I think you will you'll use them in your lab, but there's what's called boiling point elevation. And for every mole, it changes it 0.52 degrees. Freezing point depression, though, is 1.86 for a mole, which means that I change the freezing point a lot more than I change the boiling point, right? So, Sunday dinner, you're going to have spaghetti. What's going to happen? What's going to happen very first, probably? What does your mom do? Your dad, whoever cooks dinner?
Boil
Boil the water. What do they do to the water?
with the salt in it.
Put salt in it. Why?
Raises the boiling.
Urban legends.
No, it raises
It actually makes it boil
Right.
slower
Oh, wait,
Yeah.
what?
because it requires more
energy.
energy.
Will cook
Now,
potatoes faster.
that's also incorrect.
Oh.
It makes it taste different. In order to truly affect it, now might the amount of salt you put in there change it by 1/10 of a degree? Yeah. Is that going to affect how long it cooks really? No. In order to truly impact the boiling point of water, you would have to put so much salt in there, the noodles would be inedible. Period. Yeah. We tried it once.
Would you have to oversaturate the solution?
It wouldn't be super saturated, but it would be bad enough that it's like thick almost. We had I shouldn't say I had a kid one day try this in a lab setting. I was doing something. Next thing you know, I got a hole in my counter where his beaker had gotten so hot, it literally looked like it was going to melt. So he thought, well, I'm just going to pull it off and sit it on my Formica counter. Literally just melted the entire, like a hole this big in the Formica counter. That's how hot it was. Yeah. Because, salt's got a really high, and the more you put in there, the hotter it has to get. And it didn't turn out very well for
Did the
him.
glass turn orange?
Yeah, it was bad. It was really bad. So, all right. Now,
How was the water not gone?
it was almost gone. That was the problem. And it just kept getting hotter. And he left it on there forever. It was like after school. Yeah, he didn't stay after school anymore. Yeah. Okay. All right. Now, from there, we're going to talk about salvation with an O, not an A. Salvation. Okay? Now, what does that mean? Anybody know?
It's like the opposite of sticky, is what you said.
Well, kind of. No, salvation means to do what?
Elevate salt.
No. To dissolve. Now, does anybody know the actual mechanism how things dissolve? How that process really occurs?
Does it depend on what they dissociate or not?
Not necessarily, but there's two different things going on there. So here's an example. Okay? We're going to do this with salt. It would be slightly different with sugar because sugar doesn't dissociate. But for salt, so I'm going to add NaCl, right? I'm going to add NaCl to my water. Now, so NaCl is going to go in as kind of a cube, like a dice, right? Well, how does it actually dissolve? It does, but it literally is like.
They the two parts separate and then they.
Okay, but how does that happen?
It's like the Cl is negatively charged slightly, so that goes on to the positively charged end of the water molecule, and they want to be together because they're positive and negative, right? And then the same thing happens with the other one, with the Na, which is the positive, so that tries to go next to the water molecule on that part. And
The negative part. Did you watch my video?
No, we talked about this in kind of skirt in biology.
Oh, because that's like my exact discussion. So literally, you got to remember water. Water looks like this, right? Correct? Right?
Yeah.
Okay. Now initially, when I put that NaCl in, they're going to be together. NaCl, right? Then you need to think truck pulls.
Like what?
Truck pulls. Like a truck pull. You ever been to a truck pull?
Oh, okay.
Right? This water molecule floats in next to this chlorine ion, right? And this chlorine's a negatively charged particle, right? And is a positively charged particle, right? Well, this end of this water molecule is what? Negative. Little slightly negative symbol. Remember those? Well, this end then is by default slightly positive. So this end of this water molecule is going to back on up to that chlorine. And it's going to literally start to do what? Start to pull on it. It's what is called an ion dipole attraction. And as it starts to pull on it, other water molecules start to get into the nooks and crannies and get in between it and push it away. And as it breaks apart, that water molecule literally drags it out and drags it around whatever that container is. And that's how solvation occurs. Now with sugar it does similar. Sugar is covalent, which means it doesn't dissociate, right? But sugar will hydrogen bond. So instead of water ion dipoling the sugar, it will hydrogen bond to the sugar and pull that sugar away as other water molecules get in and force it apart. And then as they drag that sugar around, that's how it literally dissolves into the water.
Yeah, I was gonna ask, why doesn't like water and salt just form a crystalline structure if they bond like that? But
Because they're in different states, basically. And the fact that what happens is, it's actually kind of a cool little premise. The reason it requires more energy to boil is let's say I got a water molecule right down here, right? Right up against the flame. Well, it's going to turn to a gas, right? But to truly boil, that water molecule's got to get where? To the top, right? Well, there's all just water molecules in there. It's pretty easy for it to just split the Red Sea and boil, right? But if I got all these sodium and chloride ions in my way, it takes more what? More time, which requires more energy for me to boil, which is why it raises the boiling point. If I look at the other end, the freezing point, it's the same idea. In order for water to freeze, it's got to orient perfect. And it's got to create a structure. Well, when this dissolves, I've got Na positives here and I got Cl negatives here. They get in the what?
the way.
They get in the way. So now I've got to get colder, get it moving slower, get them out of the way for me to freeze. That's why it lowers the freezing point. And that's how both those two things work. Okay?
That makes sense.
Now, well, I try to do that. Appreciate that. Okay? Alrighty, so, hyper and hypo. Hyper. Anybody know what they refer to?
Hyper is like too much, or like hypo is like lower.
Okay, so what we're going to refer to this to is this is going to be, and this is actually, do you guys realize, I don't know, has anyone in here ever read the book? Like ever?
I've read portions of it, yeah.
Portions of it? Well, in every chapter, there is a section on the help field. Has anybody ever noticed that?
Yeah.
Yeah. Do you know why?
There's a lot of chemistry and help.
Well, yeah, but that's not why. But you're right. This class was actually a weeder class. Do you know what I mean when I say a weeder class?
To weed out people.
Weed people out. I want to be a doctor. You take this class, you realize, I'm never going to be a doctor. I mean, let's face it, medicine is like 90% chemistry, you know? So every section was designed to have that aspect into it, and so, hey, yeah, I'm not cut out for that. Now, what we're going to do is we're going to talk about hypertonic and hypotonic. Okay? And we're going to do this with blood. Okay, we're going to talk about red blood cells. Okay? Now, if I put a red blood cell in a hypertonic solution, which means that the solution has more solute than my blood cell does, what will happen?
All the solvents will leave the blood cell. And the
Water will flow where?
from the blood
Out.
cell
Out of the cell, and the cell will, do you know the word for that? Did you watch the video?
No, I have not.
Number one right there. First guy to know that answer. Good job. Yeah, first guy. First person, not even guy. First person to know that term. What's it called again?
Crenation.
It's called crenation. Okay, and that is when that that cell basically shrivels. Okay, it's called crenation. Okay. Now, I put that in a hypotonic solution.
Water will flow.
Yeah. Now, so water will flow into the cell, and the cell will lyse. It's called lyse. It's going to swell like a balloon. So you know how. So it's actually really cool if you were to be able to see this, but you know how cells, they refer to them as donuts, kind of that hollowed out part in the middle, right?
Yeah.
They will literally turn into a sphere. And the pressure will build until it literally ruptures. And at that point, that is when the cell actually does what? Dies. During crenation, it will shrivel and shrivel and shrivel and shrivel. But because all the material is still there, it won't technically die because it's still there. If I pass good water through it, it will then swell back up. Now, here's a really, I'm really kind of bummed, but I usually do this every year, and this year it's not going to work, which sucks. Okay, but that's all right. Does anybody know what this is? Nobody. It's a peach. Okay, now here's what's crazy. Okay, when this was given to me, it was bigger than the size of my fist, right? Well, the peach skin is a what?
Semi-permeable.
It's a semi-permeable membrane, right? Now it's in the fridge, so it's not doing what?
Not rotting.
It's not rotting, but it is evaporating. All that water is passing through that skin and into the atmosphere, right? And so typically, this is nothing but a little rock by now. The pit, and then whatever those cells are, right? Now, if that was the case, I put it in a beaker. And within a couple of weeks, it looks almost just like the day it was picked. Because what happens? Yeah, the water flows back in through that semi-permeable membrane to dilute it, and it literally just swells right up. It's the craziest thing you'll ever see. No, I would not. No, that one's got a little mold on it. That's why I don't think it's working right. But literally, it's usually just a pit and just a little layer, and then it just swells right up. And it's actually a really cool demonstration, but it's not small enough to make it work. But that's what happens, okay? Now,
How long did you keep it in the fridge before it does that?
usually it's there by now. I got them in October. And so usually they're there by now. I don't know why. Oh, man, now I know why. I forgot. I turned my fridge off over Christmas break. Shit. I forgot all about that.
What if we just stick it in the dehydrator?
What?
What if we just dehydrate it and then...
Probably by now it would work, but that would still take. Yeah, because they're not slices, there's not as much. But as soon as you slice it, now you're changing that skin, so now it's not as good a membrane. You know what I mean? It just changes the experiment. So you're going to do that, actually, with a plum. Not with the plum, with the prune, which are made from plums. You're going to do that in the lab. You're going to take that, you're going to find its mass, right? You're going to put it in pure water, right? Well, what's that water going to do? It's going to flow into it, right? And then you're going to find its mass later, and it should get heavier because it's going to absorb that water. And then you're going to do it with dialysis tubing as well. Like you're going to take a dialysis tube and you're going to tie the ends off. You're going to fill it full of sugar water, right? You're going to find its mass. Then you're going to put it in a beaker of pure water. Well, what's going to happen? It's going to flow in or out? In. And so when you're done, your dialysis tube should get
Bigger.
Well, you're going to see it as heavier because that water's flowing in. It's the same idea, and it's actually really cool. We're going to do all that on Friday. Okay? Alrighty, now, semi-permeable membranes. Got A, I got B. This is 0.50 molar. This is 1.0 molar. Let's say I let 5 hours go by. What's going to happen? Anybody besides Evans know this answer? Or you? Somebody knew? Nobody? Nobody? Yeah.
The solution from B will go into A.
So B's going to go to A?
No.
It's actually
A to B.
A to B. Why? It wants to dilute things. Okay? So it's going to flow from lower to higher. We're talking about just the water. Water is going to leave this and go to that. So after 5 hours, my B volume is going to be what? Greater. B is going to be up here. A is going to be down here. And if I let it go long enough, what will happen to my concentrations? They will eventually equal out, and I would have 0.75 molar and 0.75 molar. Okay? Now, what that gets into is it gets into osmotic pressure. Okay? So it's called osmotic pressure. And that is the pressure that the liquid places on that membrane. So like in yours, it's going to be a tube-like structure. It's really hard to get apart. Think like those baggies at the store.
Yeah.
The fruit baggies that you have well, that's how these are. You're going to get your fingers wet and you're going to rub them in there, try to get it to open up, and then you're going to tie a knot. It's kind of a pain in the butt, but I'll show y'all that, right? Now, osmotic pressure. Okay? Higher concentration equals a higher osmotic pressure. Okay? The higher the concentration, the higher the osmotic pressure. The higher the concentration, the lower the vapor pressure. Vapor pressure and osmotic pressure are what of each other? Opposites, right? They're inverses of each other. Okay? So that, and that is, you can look at it concentration or the number of particles, however. It's like if I go back to this, let's say I did this. I want to say this is actually off of a homework question, and it is this. If I had 5.8 molar NaCl and I had 5.8 molar CaCl2, these are my two solutions, right? And it's going to ask you for boiling point, freezing point, osmotic pressure, and vapor pressure. Okay? Now, they have the same molarity, but they do not have the same number of what? Particles, right? This one gives me 2 particles. This one gives me 3 particles. Which one is truly the most concentrated?
CaCl2.
Yeah, this one. It's got the most total particles, right? So if I said, looking at this now, which one would have the highest boiling point?
CaCl2.
This one would have the highest boiling point. Which one would have the lowest freezing point? The CaCl2 would have the lowest freezing point. Which one would have the highest osmotic pressure? NaCl would have the highest osmotic pressure?
No.
No. This would have the highest osmotic pressure, right? NaCl would have the highest what though? This would have the highest vapor pressure. Because it's got more water can leave. Okay, same idea. If you go back, let's look at this. Let me show it to you this way. If I had this, right, and got these 2 liquids. Right? This one's clearly more concentrated, right? Now, vapor pressure is a pressure it's pushing, wanting to leave against the atmosphere, right? Well, if you think about it, if I've got more particles here, at the surface there are fewer what? There's fewer water particles to leave. Thus, the higher the concentration, the lower the vapor pressure, the more energy I have to put in to get it to boil. Does that make sense? Okay?
The thing that's dissolved in fat it's not like the thing leaving?
No, it's exactly. It's opposite of the way you were thinking. Does that make sense, though?
Yeah.
Okay. Now, and really, what I wrote down in my last class is I literally wrote this: the higher the number of particles, the higher the osmotic pressure. Which would be the same thing, and then I would put the lower the vapor pressure if you look at it like that. Does that make sense, Avery?
Yeah.
Alrighty, now, we're going to do probably the hardest problem on the test. Okay? Well, first off, we got to talk about one thing. We got to talk about, does anybody know what the term saturated means?
Yeah.
What?
It means that there's like the maximum amount of particles that
Holding the maximum number of particles, just period?
the solution. Yeah.
You're missing one part at the end. Under those conditions. Why is that important? Exactly, because I can change the temperature. And if I change the temperature, I change the amount of what? Particles it can hold, right? Now, has anyone in here ever made rock candy? Okay. I died a little bit in my last class because not one person had any idea what I was talking about. Exactly. That's what I said. I said, man, you guys gotta get out more. Or I said, stay in more. And one of my kids sitting in your seat said, well, maybe you need to get out more.
You should tell them to be more like 7th period.
Yeah.
I used to use that on my 5th period to be more like my 4th period, and then it changed and it's bad, so we don't use that anymore. Now, so if something is saturated, you need to understand that it does not give you a value. Like I can't say 100 grams. I can't. Because that 100 grams depends on not just that, but it depends on the temperature of my solution, right? Because the hotter I get, the more I can hold as long as it's a solid. Remember, it's backwards if it was we talked about that the other day, didn't we? Solids versus gases, right? Okay? So, when they use the term saturated, understand, it's holding as much as it can under those conditions, which is usually at that temperature. I change the temperature, I change whether or not it's saturated. So, to make candy, right, make that sugar thing, I'm going to heat my water up, right? Put a whole bunch of sugar in it. No matter how much I stir, it doesn't dissolve, right? As the water gets hotter, all of a sudden now it does what? It starts to dissolve. So I dissolve it, till I can't dissolve it anymore. Then I cool it down. Now my solution is supersaturated because it's holding more than it should because I'm now at a new what? Temperature. Then I put in my skewer, right? And what happens? That skewer gives the sugar a place to crystallize, and that's how I make my rock candy. Okay? Now, just remember that saturated does not give you a value because the conditions change. Yes?
Same thing with like sweet tea. How like you have to get it hot first.
Yeah, exactly. Yeah. Because things just dissolve much more readily because the molecules are moving faster, right? And all those water molecules moving really fast, their truck pulling all those things away, they put it in the solution, right? As it cools down, though, they don't come out of solution unless there's something in there for them to come out with, right? As soon as you put that skewer in, now it's a place that goes, hey, let's go attach to that skewer, and now I've got rock candy. Like when I was a kid, we did it with string. You know, you put a piece of string in there, inside a day, man, it's boop, got this big chunk, and we always use cinnamon extract, so it tasted like cinnamon, just like really sweet cinnamon, I guess, yeah.
Is it like the same thing as like those like borax, like snowflake things?
It's the literally exact same premise. When we review, I'll actually show you one of them. Yeah, they usually call it like hot ice or something. You get on YouTube, it's really cool. Get on YouTube and search hot ice. It's the same exact premise. Yes? You good?
Yeah.
All right, now, the hardest kind of question you're going to run into is this, okay? So what is the molarity of a 17.5% weight to volume CCl4 solution? Now, first off, does anybody see why this problem is a little challenging? I do. But this is an entirely different equation than that, isn't it?
Yeah.
Yeah. Okay. Now, if I go back to my weight to volume equation, right? So weight to volume percent was equal to what? So mass of the solid in what? Grams divided by volume of the solution in milliliters, right? Now, so they gave me this, right? So I've got 17.5% equals, well, what's wrong with that? Yeah, can I solve that?
No.
I can't.
It could be literally any value.
Exactly. So, what these questions do is they require you to make an assumption. And if you make the right assumption, it makes the problem infinitely easier. Now, it doesn't give me my mass, and it doesn't give me my volume, right? Always assume the volume is what?
1.
Close.
10.
Is it like the
Well, remember, this is in milliliters. Make it 1,000 milliliters. Why? Say out louder. Because that equals 1 liter, and that's what I can then use right in my molarity question, and it makes the math really easy. So, if I assume 1,000 milliliters, I can go X grams over 1,000 milliliters, but I'm missing something here, right? Say out louder. Times 100, right? So what am I going to do here to do this math?
Divide both sides by 100.
I'm going to divide by 100, divide by 100. That puts it back into 0.175 equals X grams over 1,000 milliliters, right?
And multiply 1,000.
Multiply by 1,000. Multiply by 1,000. Right? That's going to tell me that my X grams is what? 175 grams, right? 175 grams of what, though? CCl4. Now, what did this problem ask me to find? Molarity, right? What is big M? Moles over liters, right? Now, this is where, as Buehler pointed out, by using 1,000 milliliters, that simply makes that a what? So I've got 1 liter here. So I've got that one. I don't have my molarity, and I don't have my moles. Or do I? I got my grams. And we've done that more than we've done anything else this year. I better be able to go from grams to moles, right? So I'm going to go 175 grams of CCl4. I'm going to times that by what? 1 mole over...
82.917.
Say that again?
82.917. Did I do that wrong?
Yeah, that's not right. That's not what I... 153.823 moles, right?
Yep.
Or sorry, that's grams. Sorry, that's grams. My moles are already in the numerator. That's grams, right? Grams are gone. What's my answer?
$1.1.
1.137, right? So I put that in my numerator. So I got 1.137 moles over 1 liter. That's going to give me a molarity of 1.14 molar. Why?
Because you have 17.5.
I got 3 sig figs there. I better have 3 sig figs there. Okay? And that is the hardest kind of question on the test. Yes?
Why do they just have you assume that it's related? That seems kind of like it could be any.
And you're right. Okay, so that goes back to what I was saying. You could assume any value.
But if it was any value, then the equation, it's a ratio, right? So it would end up as the same.
Yeah, because what I times by here, I'm going to divide by there, except it's in a volume. But what happens is because I times by that one, or divided by that 100, it literally works out. So let's say I had 500 milliliters, right? Let's just say I assumed 500. Okay, that's going to change that, right? But now this is going to become a 0.5, so it's going to divide out anyway. Do you know what I'm saying? So it works out.
Yeah, it's just any volume.
And this just makes the math easier. That's why I choose 1,000. Like, it's funny, because when I used to teach this, I always chose 500. Always. Because that was one of the containers we had in the back. It was a 500 milliliter volumetric flask, which made it easy, right? But if you think about it, 1,000 makes the math simple. So, questions? Yo.
Can we do like a raising handy one of this?
Of this?
Yeah.
Yep. Let's see. I'm going to change it just a hair, Alan. Give me 1 second. Here we go. So what is the weight to volume percent of a 1.75 molar solution of NaCl? Now, if you think about this, it's basically what?
The reverse.
It's the backwards, but we're still doing the same idea, right? All I gave you was a molarity. You've got to have a what? You've got to come up with a volume, right? Assume a volume. Now in this case, instead of assuming 1,000 milliliters, I'm going to assume 1 liter now, because now I'm going backwards. But that 1 liter will eventually turn into my 1,000 milliliters, right? All right, so let's go to 10. So I got 1, 2, 3, 4, 5, 6. Need 4 more. 7, 3 more, 8, dos más, 9, uno, 10. There we go. Alrighty, who is 5?
That was me.
Alrighty, Perkins, what do you got for me?
First, I did 1.75 m equals moles divided by 1 liter.
Okay.
And then I multiplied both sides by 1 liter, so we have moles. It's 1.75.
Okay, then what?
And then I converted moles into grams.
By doing,
So I did 1.75 moles times 58.443 grams over 1 mole.
and I gave you what?
107.275.
107.275 grams of NaCO, right? Then you're going to divide that by
1,000
1,000 milliliters now. And then I'm going to
times that by 100.
times that by 100. And what'd you get?
I think I wrote it down wrong. I think I got 102.
Yeah.
So is that 102 or 107?
It's 102.
So it's a 2, not a 7.
Yeah.
So what does that put? Well, it shouldn't change it, right? But it does.
It does.
Yeah, what's my answer become?
10.2.
Yeah, 10.2%. And I got to have 3 sig figs because I got 3 sig figs. Time is yours. Use it wisely.
That's just because he wrote it down wrong. He should have gotten it wrong.